Good morning, everyone. My name is John Gravel, Vice President of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for today's session on tools and strategies for optimal gas and flame detector placement. Today, Murtaza Gandhi of Baker Risk follows up on our fixed gas series by introducing our customers to performance-based tools to help you answer the question, exactly where should I be mounting my gas or flame detector for optimal safety system performance? In our previous sessions, we've discussed the typical thoughts and approaches to gas and flame detector placement, but those approaches aren't always enough. Our goal for today is to introduce and discuss the issues and concerns with traditional detector placement strategies, what performance-based fire and gas mapping is and why it might matter to you, how test results can be used to validate fire and gas mapping, understanding the assumptions and limitations of results-based mapping strategies, and we'll also have time for you to ask Murtaza your questions. Our speaker has over 15 years of experience in the process industry, performing automation, instrumentation, and safety instrumented system projects. Murtaza Gandhi currently serves as Senior Process Safety Engineer with Baker Risk. He regularly leads both qualitative and quantitative studies, including performance-based fire and gas mapping. He serves as Supervisor for Process Safety Operations in Houston, manages the controls and instrumentation systems, equipment, and programming at Baker Risk's Jet Fire and Dispersion Test Facility in Lavernia, Texas. He brings us great experience and insights, and we welcome him. Quick housekeeping point, we'll be muting the phone lines, so if you have a question, please use the question tool built into GoToWebinar, and we'll get them answered. With that, I will turn the presentation over to Murtaza. Murtaza, take it away.
Thanks a lot, John. Thanks, Lesman, for inviting me to do this presentation, and thanks all the attendees who are signed in and who have joined in this morning. The topic is a very interesting one today. It's the tools and strategies for optimal gas and flame detector placement. This is a topic very close to my interest, and I'd love to talk about it. And this is a great venue for me to connect with some of the users who will be using some of these technologies going forward. So the topics that we plan to cover today are the basics of fire and gas detector mapping. So these are some of the introductory slides that most of the attendees might be already familiar with. But just to kickstart our discussion, I will be going over some of the very basics. We want to talk about the shortcomings of undertaking a traditional approach, which is generally a prescriptive type of approach or an experience-based approach. We will also be talking about performance-based detector mapping, just as John mentioned, how and where to put these detectors and how to quantify the success of these detector mapping is where the industry is now moving towards, and it's also crucial as a part of your risk management plan. Importance of testing to validate the results. So once we start doing these more scientific-based models and use those for fire and gas mapping, it is also important to understand what the limitations and the assumptions are and how can testing help validate some of those results and help us get better in making our models align with the real life. And then finally, we want to talk about the fire and gas detection life cycle and assist life cycle, since a lot of the life cycle is aligned, and what are the key things that the fire and gas detection life cycle also need to consider as they would in assist life cycle. So understanding the basic flame detector, you have all the attendees are already familiar, and many of your facilities do or probably have a lot of these types of flame detectors. But simply speaking, these are the sensors designed to detect and respond to the presence of a flame or a fire. And you will see them, on compressor decks, in process areas, in buildings where there are potential for fire. And it's important for a quick detection. These are of different types. The ones that are predominantly used in the industry are the ultraviolet type, the infrared, and the UV or the IR type. There are some also now with redundant IR sensors, so they're called the triple IR sensors. And the idea is that these sensors give you an early detection of an incipient fire so you can prevent an escalation and do something about it. Similarly, gas detectors are devices that detect the presence of gases in an area. They are often a part of a safety system, so they may be connected to a shutdown system, or they may be connected to your fire protection system, to an alarm system. There are different outputs from it. These can help with early detection of different types of gases. So some of the main consequences that you're looking for are a gas release that can cause a fire, or a gas release that can cause an explosion. If it's a toxic release, it could be, of course, impactful to personnel. And then in certain areas, you may also want to look at oxygen deficiency and the impact of that to personnel. The types of detectors that are predominantly used in the industry are electrochemical, the catalytic bead type. The catalytic bead type are still used for sensing hydrogen and other such gases. IR is the most common one that's used right now. So you will see point IR detectors scattered throughout your facility. Photoionization sensor, and you may also have used ultrasonic sensors that pretty much look like a microphone, and they can cover a wide swath of area and help with very, very early detection in many cases. So what is a fire and gas detection system? Say you're trying to sense something whether it's a gas release or a fire, and make an action based on that information. So the output can be an alarm, or you may shut down a process, or you may activate a deluge system. You may start an evacuation process, depending on what the severity is and what the risk is from that scenario. You and your emergency personnel will take the decision to mitigate the hazard or to evacuate if necessary. So here I'm just showing an example of a propane bullet that's connected to a pump, and the propane pressure at the outlet is 1200 psig. If you have a seal leak from this propane bullet, from this propane pump, which is in the direction of the propane bullet, then you could end up in a levy type scenario. So if you have a fire detector that's also connected to a deluge on the vessel that can help keep it cool and at least delay the escalation, then that could give enough time for your firefighters to come in there and help you minimize the impact or minimize the chances of a levy. So this is just a normal block flow diagram of what would happen. So if you have a release that ignites, then you detect the fire, then either your deluge comes in and starts cooling this down, or you report and you would also report the fire. You would dispatch your ERT, and then you would set up to firefight and actually prevent the scenario from occurring. So the early you can detect, the more advantage it gives you in reducing your potential risk. So to demonstrate some of these points and get us all started, I have a few videos to get us calibrated as to what can these leaks or fires look like. So this is an example of a flange failure test. Here, there is a flange here that's coming from a saturated propane supply. This flange has been, one or two bolts have been loosened slightly on the bottom side, and you can see the impact because of it. So in this slide, what you saw was that to give you a perspective, this pad that the concrete pad that you see is 80 by 80 feet, and just a small flange leak from a relatively low pressure release at a relatively low flow rate, you can have a pretty big cloud, maybe going up to about 40 feet or so, and expanding. And depending on the wind direction and the wind condition, you may be able to drag that and go much further with it. This is a jet fire test. So it is with saturated propane, again, a 3/4 inch orifice, at again relatively low pressure. The flow rate is higher in this case. So again, in that case, the release was at a relatively low pressure. But the flow rate was higher, and you could see that the cloud went significantly away from the release point, which it was almost up to 60 feet. This is just a thermal video of that same scenario. So this is the release, and now the fire occurs. So you can see that the fire can be massive, even from a 3/4 inch type release. You may ask me, why am I showing an explosion video? But we do normally come across scenarios where gas detectors are placed in buildings with hydrogen or other extremely flammable material, and the idea is to initiate a shutdown very, very quickly based on it. And what can a few seconds do is what you're trying to identify. So this is called a deflagration load generator, and this is a high-speed video of that. So you can see that the impact of an explosion, as you may all be aware, is massive, but is also very quick. And so the action sometimes need to be very, very deterministic and very, very quick. And that's what we are trying to design. So locating fire and gas detectors. As I mentioned earlier, there are different types of detectors. There are the acoustic, the gas, the fire, and there are other types of detectors available as well. The location of those detectors, how do you start with that? So you can do a qualitative analysis. So based on your experience, you can walk around the facility. Sometimes insurance risk engineers will walk around and identify spots where they have been to numerous facilities and they have seen lots of insurance claims of where the releases occurred and what type of damage happened. So you can start with that approach, or you can also start with the facility siting type approach, which is determination of the hazards, what type of consequences occur because of it. So do some consequence modeling, do some risk modeling, and determine what the consequences and the risk are, and then based on that, make decisions about where you will place your detectors. Why are these studies so difficult? So this is a very interesting note from HAC. 8 years of offshore data they collected and said 60% of known releases were detected. So it is a pretty low number if you can think about it. And this is all combination of visual, any type of detectors, any other means of detection out there. So the challenge is there is no real industry standard. There are some standards on the IEC level. There are some practices, but the users are still struggling with what is the most optimal, what is the way what is the way, or what is the approach I need to take. So traditional studies are more experience-based, or you can go the other way, which is a very extremely quantitative CFD modeling. Now, CFD modeling is going to be needed for stuff that is inside buildings like warehouses, etc., where the where normal consequence models is not helpful. But you don't want to do a CFD model for every single scenario because it greatly exceeds the cost of putting a detector in its place. So there's a balance somewhere in between those two approaches. So IS-84, which is, as you may know, a standard under the International Society of Automation based on safety instrumented system, they generated the first version of a technical report on performance-based detector mapping in 2010, and then an updated version was developed and released late 2018. Uh, but that gives you an idea of how your performance-based detector mapping works. So that gives you an idea of if I put so many detectors, what is the value of it quantitatively in terms of my risk reduction? Can I take risk reduction in my LOPA? And can I consider those scenarios and reduce the risk by placing these detectors, or are these still just supposed to work as an in as an initial way of alarming and letting me know of some sort of a problem out there? So that's kind of where the standard or the technical report does not tell you exactly that this is how you place the detector, but it gives you a pretty good idea on what things you should be looking for and how you should be calculating that. So here is so the three main components are the detector coverage of how well your scenarios or your area is covered. How well is your safety system working on it? So many times these detectors are part of a PLC or a shutdown system, and you're trying to identify what is the availability or what is the reliability of that safety system to take the signal from the detectors and then initiate a shutdown, initiate a mitigation action like a deluge, or generate an alarm, etc., etc. So as you can see here, you develop an event tree, which is your initiating event. As you may see from our previous case of the levy, that could be a fire as your starting point. Then an ignition occurs. So what is the probability of that? What is the fire? What is the probability that it occurs towards the tank? What is the success of that fire detection? And also the response. This is a critical piece that gets missed many times. How effective is your mitigation to prevent that escalation? Because a release has already happened, a fire has already happened. So how do you determine success, and how well can your system take you to that successful endpoint? So, like in this case, you ended up with no major fire. So fire still exists, but no major fire is what what your end result is, or what your success factor is. But a levy or a fire escalation and levy is a catastrophic consequence, and that's what you're trying to prevent. So the types of approach under IS-84 TR7 is geographic and scenario coverage. Scenario coverage indicates the number of hazardous scenarios inside a facility. So any different types of sources within a facility could be considered a possible release location. And how many of those can you identify with your detection system? Or for a geographic coverage is how much of an area or a volume you can cover with the detectors if a release or a fire occurs. Challenges with calculating the scenario coverage. There are some real challenges with geographic coverage because it creates a grid-like structure and may add to a lot of detectors, which may also result in nuisance alarms or trips. So you want to be cognizant of that. So now if you say, okay, I want to go with an approach that is more science-based, more model-based, and so you want to go with a consequence approach or the scenario coverage approach, but you have to understand what the limitations are, what are the challenges with it. So it depends on the number of scenarios identified. So if in a facility, if I say I have only 2 scenarios, and if I catch those 2 scenarios, I have 100% success. But that's not right, because you may have hundreds of thousands of scenarios. So what are the right number of scenarios? It also depends on the fluctuations in the plume concentration. So if you have a release and if there is a wind gust, then how does that impact the concentration? How do you model crosswind and upwind releases? So if you have winds going in the crosswind or the upwind direction, are they being able to be detected by your detectors or not? And then different detectors have different response times. So when you purchase any type of equipment, uh, you know, you may ask those questions about what are the response characteristics. Some of that is already on the spec sheet, but you may need some more information to make that determination yourself. So to answer some of those questions, we said we will want to run a series of tests at our test facility and identify for ourselves what type of coverage, what are the limitations that we were seeing, and how to improve our internal model to generate that map, which is more realistic and more beneficial to the users. So we performed a series of tests. About 74 tests were performed, ranging from about a minute to a minute and a half. And we placed 14 detectors from 3 different manufacturers, 60 to 200 feet from the release point. Now the question may be, why place these detectors that far? Because again, as you can see, these releases were of different sizes, and we wanted to keep a consistent set of detectors at same location and identify whether those detectors are able to successfully detect different size of release, different direction of release, or not. So we did 5 different orientations. We did one in the downwind direction, one which was going up, one was going down, and one was going crosswind in east and the west direction. This is the grid structure. So where you see these dots are where the detectors are placed. Again, this is an 80 feet. So this is, about 60 feet, 80, 100, so on and so forth. And we went up to about 200 feet. So I'm just showing a case study of one video for the downwind direction. So we had detectors here, and you can see that depending on the wind, now it could be, it could jet out like this, and we would be able to see it very quick. Or if the wind is relatively calm, then it takes a while for the gas to reach the detectors. So on the half-inch test, this was our observation. We found that for 1 out of 1 detectors, the scenario coverage was less than 60%. Now that gradually increases when you have larger releases. So for 3/4 inch, it's much higher. For 1 inch, it was higher than that. The scenario coverage for 2 out of 2 detectors was observed to be less than 40%. So where at least 2 detectors have to catch it, it was pretty low. Most of the releases in the up or the west direction were not detected. That tells me that I may have to place detectors at different locations to cover releases. And if I'm concerned about releases in not in the predominant wind condition or the predominant wind direction, then I should consider those in my model as well. A wide-ranging fluctuations were observed. So we did these tests at different times of the day and different weather conditions to observe the fluctuations, and we wanted to account that fluctuation in our calculation as well. Then the speed of the rise and the maximum concentrations varied significantly between detectors as well. So if you had some detectors that respond very quick, some had a slightly slower response, and then the concentrations varied as well. So with all that information, how to perform a fire and gas mapping system with scenario coverage, this is just a general approach that many industry practitioners use who use the scenario coverage approach. Of course, for geographic coverage approach, it may be slightly different. As I said, you may have to form a grid. So this approach, you start with the development of a model, and that model I mean is a 3D model of the facility. You import your consequence and risk contours to aid in the fire and gas detector placement. So you take in your flammable contours, your toxic, your thermal, and your risk contours, and then you place them on your plot plan and identify based on it where do I need my detectors. So generally, a unit survey is conducted to determine the dimensions of major equipment and structures. This is true for brownfield facilities. For greenfield, you may have models that are already built in 3D, like from Navisworks or AutoCAD 3D. Depending on different softwares out there, some some may be able to take some of those directly. The current models, the current consequence models, do not really consider the obstructions significantly. So these models are very critical for your fire detection. But for a gas detection, you may want to consider them for like inside buildings and warehouses. But for outside areas, you may want to place the detector clear from obstruction or clear from vessels around that area. So this is a general plot plan of an example facility. And this is a 2D model where these are all the different vessels. This is a building, and this is a pipe rack that you take in and create this structure. And so this is a 3D model of the facility where you can take all these different obstructions and identify if I place a fire detector here, can I see a fire in this area or not? So, or if you have a gas release in this area, and if you put a gas detector underneath the pipe rack because you assume that there will be some accumulation there, then you can run your contours on top of it and identify whether you will be able to see the detector will be able to see the release. So then the contours are imported into the model from the site consequence models, and the flammable contours are imported at UFL, which is the upper flammability, lower flammability, or the half of that. Similarly, toxic contours are imported at values of appropriate probability concentrations. So for H2S or for ammonia or other toxics, you may have to import the contours at those different probabilistic values. Similarly, for thermal contours, the values are imported at 4, 12.5, and 37.5 kilowatt per square meter. So most guidance in the industry says that about 4 to 6 kilowatt per square meter you can approach for about a minute in your fire retardant PPE to operate a valve, to push a shutdown button, etc., etc. At 12.5, it is you can in some cases you may be able to approach with bunker gear or with fire protection gear, which is specific for rated for that, and then 37.5 is uninhabitable for humans. And then you also import all the risk contours, so flammable, toxic, and thermal. And you can see that these contours overlay on your plot plan. Now these can also so the contours are the green one is your half LFL, this is your LFL, and this is your UFL. And then based on it, you can determine that this particular piece of equipment has a higher consequence. Now, if you went risk-based, then you would say, okay, I have this equipment and the consequence looks pretty bad, but the frequency of a release here is extremely low because I don't have any flanges. I just have welded piping here. So then you can consider that in your calculation and determine whether I want to consider protecting this detector with a gas detector or not. But for here, it may be where there are lots of flanges and there is also a pump underneath which could have a higher leak potential or higher potential for fire. So you may place more detectors in that area. Similarly, for toxic, now these These contours are all cumulative, so it shows you for the entire releases from all these different areas. But you can also draw this for individual pieces of equipment and determine what needs what type of coverage. Similarly, thermal contours, as I said, the three values that are of interest are 4, 12.5, and 37.5 kilowatt per square meter. These are the societal risk contours. So these use, the wind direction. So what is the predominant wind direction? What is the equipment failure probability? What is the weather? What is the wind? We already considered the wind. So what are the weather stability factors? So based on that, you can generate these, and you can, as I said, you can also generate those contours for each piece of equipment and determine what is above your tolerance criteria and how you need to protect it. So I've kind of already covered this, but the gas detectors are point gas detectors, and you place them at a certain location with the height and the coordinates. Line detectors or the line of sight detectors can work longer distances, used for perimeter monitoring as well as for certain areas that there are lots of leak sources, and maybe it's by a road, by an internal or an external road, and you're trying to prevent the release going further away. Acoustic detectors are the ultrasonic detectors that I mentioned earlier. And then the fire detectors generally work in a cone-shaped coverage pattern. So here, some example gas detectors shown here, and then these are the line detectors. Similarly, for toxics, you're trying to prevent. So you determine that these are my toxic sources. So you provide toxic detectors on those particular vessels. And then fire detectors where you think there is a possibility of fire, or that if the release happens and you're trying to cover, if there's rotating equipment over there, there's a higher likelihood of fire. There are certain ignition sources like maybe permitted work, etc., may be more frequent in that area, so you may want to consider additional fire detectors there. So this is a completed model in 2D, and then this is in 3D. So here you have gas detectors, toxic line detectors, flammable line detectors, you have fire detectors, and then based on that, you can determine what areas or what scenarios I still want to cover beyond this, or you can prioritize it based on risk and identify these are the ones that I want to prioritize right now because I have a finite budget, and I and I may do, or I want to do the other detectors maybe later. Then what gives you the most value for your money? You can do it risk based and identify these are the ones that I want to target right now. So the last point is the comparison of fire and gas system and the SIS life cycles. This is from the TR7 document. The most important thing here is to first identify what your philosophy is. What are you planning to do with it? Are you trying to alarm, or are you trying to do an immediate shutdown? Are you trying to evacuate? Are you trying to operate a deluge valve? What are you trying to do? And that depends on different types of hazards and the risk associated with it. So once you identify those things, then it gives you an idea of how I'm going to approach my fire and gas system. So for the assessment section, you will identify the areas of concern, what are the hazard or the risk scenarios. You'll identify what are the consequences, those contours that you just saw. What is the frequency of a release? So as I said, in many cases, the consequences may be really bad, but the frequency can really, really be reduced by your safety systems, by your other mitigation that you may not need to prioritize that. So that, it's a risk-based approach. This is a consequence-based approach. This is a risk-based approach. And then you can assess how you want to go for it. So whether you want to do consequence or risk-based, you identify this is what I'm trying to protect. And then you go to the drawing board and develop a performance requirement and a conceptual design. So this is your engineering stage where you identify these are my specifications of this is what I'm looking for. And then you do a verification. So some similar to that event tree that I showed you earlier, you identify what the detector coverage is for a particular scenario or for a particular geographic area. How good is my safety system in taking those signals and doing something about it? And if it does successfully start the action that I've designed it to do, whether that's effective or not, and if it is effective, does that mitigate my risk or not? So it's a pretty lengthy approach, but it gives you more than just a prescriptive type idea of what you need to do, where you need to place your detectors, and where can I get the most risk reduction from. This is the SIS life cycle, and this comes from the IS-84 document, standard document. So as you can see, some of the similarities here is you always start with a hazard and risk assessment. So many of you might be familiar with HAZOPS or process hazard analysis that's done to identify what the hazards are, and then you identify what is needed to prevent that hazard. So the difference between the SIS and the fire and gas system is in the SIS, you're trying to keep everything within the pipe in the first place. Now, you may use SIS for your fire and gas system, but in general, for your process safety functions, you want to keep everything within the pipe. But in your FGS life cycle, you start with the assumption that a release or a fire has already occurred. This step is pretty similar. So this is your engineering design phase where you write the specification of what my safety system requirements are, how I'm going to design it, how I'm going to operate it, how often do I need to test it and maintain it. That's part of your engineering design spec. And after the verification is done, that safety system is going to provide you the risk reduction that you have designed it for. Then you start putting the system in place, you operate and maintain it, and then every time you need to modify it or you need to decommission it, you go back and analyze these steps and make sure that it still is keeping the process in the safe state. The thing that's kind of implied in this life cycle is the steps after that. So once this is all your engineering phase, and you determine, okay, this is what my system is going to look like. Now, how often do I need to test it? How do I calibrate these detectors? What is my function? So let's say it operates a deluge every whatever period of time. Do I need to simulate a signal from my detector and go all the way up to initiating that deluge system? So that's something that that also needs to be determined. And so these two life cycles kind of have to work together to an extent and use some of these ideas that have been described in the IS-84 on the installation and commissioning in your FGS life cycle. So the two life cycles kind of follow the same path, but there are certain differences in the assumptions, and you want to make sure that you follow the correct steps. And then once you do that, how you maintain and calibrate those detectors and operate the mitigation portion of it is crucial as well. So that's all I had for it's. I think I've run over by about 5 minutes or so, but I'm happy to take any questions at this time.
Murtaza, we've got a couple that have come through. First question was, how does the approach change for non-standard processes? Do you match a particular approach to a particular industry segment?
Yes. So depending on what your what your facility looks like. So let's say if it's a paper mill or a wood manufacturing or a wood processing facility, you may have different types of hazards. You may have some combustible dust as your hazard. So in that case, the approach kind of remains the same, that the life cycle remains the same. What are the areas of concern? What am I trying to protect against? And then based on that's why this step is very crucial, because the depending on the industry, the the types of detectors, the types of shutdowns, the type of action may differ, but the overall idea is to prevent the escalation of whatever has already occurred. And so that's something that you start with right here. So I think that's so the life cycle is kind of common for different types of industries, but you have to approach it for the hazard that you are mitigating.
Okay, thanks. Another question we had was, can you take credit for this in LOPA? By taking this approach, is there a way to take credit in the LOPA?
Very interesting, and that's one of the questions that we get asked all the time. The thing that you always have to remember is fire and gas system. The initial starting point is that a release or a fire has already occurred. Now, the TR7 does give you some guidelines on when you can claim a fire and gas system as an IPL. If you look up the document, it needs a minimum coverage value of 90%, and at that point, and this is for the entire loop, right? So you say, okay, my detector coverage is 90%, but do I have my mitigation? That can I say that when I do shut down based on this fire or gas detection, is my safety system okay for that? And if my mitigation is effective or not. If you can claim all that, then there is a way to do that, but you have to be very careful in how you approach it, because it's finally something that you have to be very comfortable doing it. There is approach in the guidance document, the TR7, that can help you do that, but the approach needs to be handled carefully.
So a follow-up question to a comment I think that you'd made just then: how does mitigation effectiveness play a role in the mapping? So how do you calculate the impact of mitigation performance?
So it goes back to my so the mitigation effectiveness is what am I trying to prevent? So in my case, my example of the levee scenario, my mitigation was, so the fire has already occurred. I know that, I'm going to have some damage, but if I'm trying to prevent a massive levee that can cause catastrophic damage at my facility, then that's what I'm trying to prevent. And if I do that, then maybe I can claim that as my success, because that's what I have designed my system for. First of all, I didn't want my pump to leak at all. So I have put double seals on it, and I have alarms on it, and I'm going to try to do as much as I can to keep that release in the pipe itself. But unfortunately, it has happened, and now my action is to prevent that levee. So for me to calculate that mitigation effectiveness, if I have that in my mind, then I can start identifying the different means to prevent that from occurring. So, if the fire, like in this case, the fire is towards the tank, so this was based on the wind directions, that the fire is in that direction, then my success factor of the fire detection was 70%, sorry, 7% in that case, because I didn't have a detector. It was going to be visual at that time. This is a manual action one. I have one similar to this for automatic action, where this would be close to 90%. And if I did get a successful detection, then my firefighting was adequate. My deluge was adequate. If my firefighting was adequate, then I can say there's a 50-50 chance that this is not going to escalate into a major fire. But let's say if I did this whole thing within a minute or less, in a few seconds, and then I started the deluge, then my response success is going to go up significantly. So I may not result in a major fire most of the time if I can detect it in a very, very quick manner and mitigate it. But if it takes time where somebody has to see the fire in the field, by that time your fire might have already become bigger. So now it's harder to mitigate. And then now I have to deploy the firefighting. It takes finite amount of time for the firefighters to go out there. Then my success, the chance of success keeps going down, and I may end up in a levy in that case. So that's what you're trying to consider in your mitigation effectiveness.
Got it. Okay, I didn't see any other questions. Murtaza, thanks very much for the presentation, and thanks everybody for participation. For the group, if you have any specific application questions, please feel free to give us a call at 800-9-LESMAN, 800-953-7626. If you don't know your account manager, feel free to ask for me, John Gravel. I'll make sure you get taken care of. I can also be reached at johng@lesman.com. If you want to know more about the technologies we supply and support, all of these webinars are posted both on our website and our Lesman Instrument Company YouTube channel. A personal request, if there are topics you'd like us to cover in our future webinars, please let me know that as well. We have access to lots of application and process experts. Let me know what we should cover by emailing me at johng@lesman.com. At this point, if there are no further questions, our presentation will conclude. Thank you everybody for attending, and have a fantastic day. Thanks, Murtaza.
Thanks a lot, John. Thanks for inviting me.